is, as Anele mentioned before, black carbon in boreal forests, origin, fate, and environmental impact. I'm affiliated with the Institute of Forest Ecology at the Boku University in Vienna, but my second affiliation is the Austrian Academy of Sciences, where I'm actually physically sitting right now. I will give you brief information about the context of today's talk, because I'm not explicitly talking about black carbon, which you might hear about. So black carbon is defined as remains of incomplete combustion of fossil fuel or any organic material, such as biofuels and biomass. But I'm more focusing actually on pyrogenic organic carbon, which comes from wildfire and pyrolysis reactors. I will start with the wildfire aspect and later on move to artificial pyrogenic carbon, if you will. I will talk about the characteristics of this kind of carbon and their environmental impact, specifically in context of boreal forests. And I will also come to the point where we talk about engineering by utilizing pyrogenic carbon for environmental management. So we start from the natural origin towards the artificial origin of such carbon. And I mentioned black carbon. You may think about, so as Arctic researchers in specific, you think about airborne particulate matter that is distributed. And my topic has actually to do with this. And I will come back to this later on to show you the context between this black carbon and forest fire in general. Forest fires occur regularly in boreal forests. They also represent the principal disturbance regime. There are more such as insect infestations, for instance, or even human impact has become a major disturbing factor. But wildfires are still the most prominent disturbing regimes. Actually, 1.1 to 1.5% of boreal forests burn each year. And you can sum this up and you will come to the conclusion that in a century, roughly all these boreal forests experience wildfire. And this is important in terms of a global carbon cycle. 30 to 40% of all this terrestrial carbon is stored in boreal forests. And this corresponds to 60% of all forest carbon. And the major share is not in the above ground biomass, but it is actually in the soils. The soil moisture regime, the fire intensity, and the rotation cycle of these fires, they are key determining factors for the carbon budget. And we also know that there's a challenge of permafrost thawing due to climate change, and therefore climate change is the driving force behind changing fire regimes. Just to give you a number to make this even more clear, a decrease of only 10% of soil organic carbon would be equivalent to all the anthropogenic CO2 emitted in 30 years. So this is really a lot, and we are talking here about a major carbon resource. So I've prepared here a slide that shows you actually current wildfires. It's taken by the MODIS satellite, and this website, Global Forest Watch Fires. It was accessed only yesterday. You see that at current, if you look at the boreal forests, there are just a few fires in Canada. There are not much in Northern Europe, and there is a hotspot in eastern northeastern Siberia. This corresponds very well to the recent incident there. You may hear it in the news that there was a huge oil tank collapsing because of the melting of permafrost. And this corresponds to an area where we have a temperature anomaly currently going on with exceptionally high temperatures. And this leads also to the wildfires you can see here in northeastern Siberia. And if you look at the current particulate matter in the atmosphere, this is also data from just yesterday evening, we see currently at PM 2.5, the global hotspot is exactly in northeastern Siberia, where these wildfires are going on. And of course, this is a major source for black carbon. And this closes somehow the loop, which I mentioned earlier. Wildfires, pyrogenic carbon, which I'm talking today, is of course correlated to black carbon emissions as well in terms of particulate emissions. So let's come a little bit from the global kind of view to the local aspects. Here is a picture of a tree that was obviously subject to wildfire, actually 2 times, as we can see at the scars here. In the Barrier, very close to the Barrier Subarctic Research Station. And what we see is that obviously this tree survived already at least 2 fires. What are now these primary factors affecting char formation? This pyrogenic carbon, which I mentioned before, is also coined as char, not charcoal, because charcoal is artificially produced, but naturally occurring it is called char. And the formation of char is influenced by the type and quantity of biomass and the fire severity. Lower amounts of char are produced in high severity fires compared to fires with low or just moderate severity, as higher temperatures during these severe fires lead to a more complete combustion, less char and more ash. The amount of char in boreal forest, just to give you a number, a rough number, ranges between really very tiny amounts, 0.02 kilogram per square meter, and up to 3.4 kilogram carbon, just carbon per square meter. If such a forest site burns, the stands are regenerating, and this regenerating process, of course, also depends on the severity of the fire. We differentiate 2 major types. The surface fire, which is just on the ground, burns shrubs and grasses, some biomass that is on the floor, and the trees, the larger trees can survive, as you can see here in this picture. But if you have a crown or a crown fire or a stand replacing fire, which is usually a crown fire, then the regeneration takes, of course, much longer. Lower amounts of char are produced, as mentioned before, and stand regeneration is only possible by usually by seeds that are spread. But in this picture here, you can hardly see any char, despite the fact that you see it on this particular stem. So there is it, and now let's look at it from a soil sciences perspective. For this purpose, I'm showing here a soil profile. that shows a typical podzol, which is a very common soil type in boreal forests. And at this particular location, we had a wildfire 160 years ago, and no fire since 160 years. Dominant species here are Scots pine, as you saw in the previous picture, and for the tree, for the crown layer, and a moss called Pyrolysis schreberi. You can see it on the top left here. That's Pyrolysis schreberi. What we see in this profile is an organic horizon of about 5 centimeters, more type humus, and just at the interface between this organic layer and the mineral layer, you see this accumulation of pyrogenic carbon from the fire 160 years ago, is roughly 1.5 centimeters. If you go through the profile further, you see the alluvial horizon, typical for iron and aluminium depletion. That's why it's pale color. A slight humus accumulation, followed by the BS horizon with reddish orange color as a consequence of iron oxides and aluminium oxides and their hydroxides that are accumulating there. And then it goes to the parent material. So what I want to highlight here is that although the fire here is 160 years ago, the pyrogenic carbon is not really integrated in the mineral soil horizon, but indeed most rests on the interface. Of course, there are particles and water flow and with bioturbation, which is also limited there, but it occurs. You have some translocation of this pyrogenic carbon into deeper soil horizons, where it is, of course, more stable, protected from decomposition, protected also from fires that occur later on. But this is obviously a very slow process, and most sits here at the interface between organic and mineral soil horizon. I mentioned that this pyrogenic carbon is recalcitrant to microbial decomposition. And this is also an important, if you will, an important precondition for the discussion of its stability. And I'm showing you here in this slide why this is so. The chemical process of pyrolysis is very simply explained as you heat this biomass and you exclude oxygen, otherwise it's completely burning, or you limit oxygen. There, first of all, what's happening at lower temperatures, water will be removed, followed by volatile compounds, and at around 200-degree hemicellulose starts to degrade, cellulose a little bit later, 240-degree, and lignin, which is the most recalcitrant, at around 280-degree. What's happening from a more amorphous stage of carbon, we will end up with more orientated structures, so-called fused aromatic structures, and those are very resistant. You know that from archaeological studies, you could trace human settlements mainly because of remnants of charcoal at the fireplaces, and this can sustain in the soils a couple of thousand years if the conditions permit. Now let's come to the first study. We started in not in Finland but in Canada, and the Canada permafrost region, and we set up a fire chrono sequence. So we were looking at sites with recent fires. We found one where 3 years ago there was a fire, 25, 46, and 100 years ago. We were looking specifically at 13C and 15N, so the isotopes were very helpful. And The wildfire advance thawing of permafrost by burning the insulating organic layer and decreasing surface albedo. This was one of the key findings. In the topsoil horizon, we found that the recent fire areas contained a smaller fraction of labile soil organic matter and were slightly more enriched with 15N and 13C than in older fire areas. So basically what's happening during a fire is that the labile fraction of soil organic matter burns away and the more recalcitrant fraction stays. And this is largely accounted to the accumulation of pyrogenic carbon. Soil organic matter in soils at the permafrost surface could be mainly recalcitrant, and its decomposition is not particularly sensitive to changes resulting from fire, and this is actually good news. The carbon emissions consequently from the mineral permafrost soils could be limited. And this is, as I said, this is actually good news, but unfortunately we are living in a complex world, and it's not only good news because at the same time, the permafrost has less time to recover after such fire and reach its original depth, and therefore the permafrost soil organic matter, although it is possibly recalcitrant, or we saw signs that it is recalcitrant, is still vulnerable to decomposition for longer periods of time, simply because it is not locked in permafrost and therefore unavailable for microbial decomposition. So over time, there could be decomposition still going on, although it is, we think it is quite recalcitrant. So from these natural wildfires, we were actually starting to think about questions like, can we consider boreal pyrogenic carbon storage strategies safe? So is what we found, does this mean it's good news in terms of climate change? Do we have a solid tool for national carbon accounting compatible with these IPCC strategies such as BECCS, bioenergy, carbon capture and storage initiatives? What are the opportunities and threats? Could we actually add, and what you see in this picture here, could we mimic wildfires by spreading pyrogenic carbon on the soil surface, and then does it mean it is stable and contributes to recalcitrant carbon in the soil? So rather than burning, just add pyrogenic carbon. Yeah, and what we found as well, and this is basically the link between these natural fires and artificial carbon input, that boreal ecosystems, they do have a long history of wildfires, and as such, they are prime study examples to understand these long-term effects of biochar amendment, because biochar, I didn't mention this, carbon that is, or pyrogenic carbon that is produced in pyrolysis reactors, and with the aim for environmental management, such as carbon storage, for instance, is called biochar. And we spread this in the forest with the aim to, so one aim could be just long-term carbon storage. But such experiments are not, so they are not done since a long period of time. So we have limited experience with long-term behavior. But we can use these wildfire systems, boreal forests, to see what is actually happening with pyrogenic carbon over long periods of time. And this is basically what's stated here. Now, when you, other than a wildfire, when you just spread pyrogenic carbon on the soil or forest floor, not even the soil surface, but the forest floor with, of course, vegetation, you can imagine that it is different to a wildfire where basically there's no more ground vegetation or little ground vegetation left. So our aim was to ask at the first point, what is actually happening? What is happening? Is it stable? Does it stay where it is? Or does it move? Is there substantial erosion? And I try now to show you a video. We did this in a site in Austria. We spread biochar on the forest floor. Okay. All right. So let me pause this. This was July. So we started the experiment in July, set up a time-lapse camera, and you see what is happening with time. So on 24th of July, for instance, I'm zooming in here.
We can't see the screen that you're playing.
Yeah, unfortunately.
Okay, you can see. All right.
I think you have to stop sharing and then share on your new video screen.
Thank you for this. Let me. Okay. All right. Can you see it?
Yeah, now we can see.
Okay.
Good.
So we start with wind events on July 24th. It was not too strong, and if we so there was a little particle movement, but it was not terribly much. Then a couple of days, nothing happens. July 25th, we have precipitation, and you see it is actually moving. I'm always zooming at this particular location because there is fewer grass, and therefore one can see this movement more clearly. There was a strong wind just now, and the particle movement was also obvious. What you can see by time now we are already in August is that over time the vegetation grows, the mosses grows, and somehow lock these single particles in and protect them from erosion. What is also obvious is that if events of precipitation, these particles tend to move more as compared to heavy winds. And this effect becomes even stronger as so with time biochar particles rest on the ground. Meanwhile, we have September and October. You can hardly see any particles on the surface, and therefore the movement becomes also less. So soon we will have the first signs of winter. Snow is coming in November. Snow is then thawing again. And even though we have here a very strong storm event, there's almost no more movement. I'm making this a bit faster. Just a comparison, one day after application versus 134 days after application. So what I wanted to show you with this is that one has to clearly think about when is the optimal time of. No, this is just pure. Sorry, YouTube continues to speak at the background, so I have to stop this. Okay, what I wanted to show with this is that there is actually a there's a specific. You have to look at the optimal time when you spread this biochar, and this is basically in times when there's not too much wind, especially in the times just after spreading. When it becomes dry, then you have problems with wind erosion. And the second aspect is that if you have precipitation, a lot of precipitation, it somehow secures this biochar, and it also helps to wash smaller particles down the profile in the organic horizon. Of course, this is only a limited application in terms of forest fires, because you can never control this, but it has some very interesting results. Carbon flux. We, of course, then looked at what is happening with the carbon, the soil respiration. And this is from the case study in Austria, where we see that there is an initial stronger flux from these biochar sites, but then it remains more or less the same. You have to look here at the relative difference, not at the absolute values, because here it's winter time and of course the flux is lower. But as you can see, there's not really a significant difference, and it's also fluctuating, but we didn't see a priming effect. So the addition of pyrogenic carbon did not interfere with the carbon that is already in the organic horizon. The same thing was found in Finland, where we have two plots with 5 and 10 tons per hectare. The previous study in Austria was only 5 tons per hectare. And you can also see that there is, relative to the control, not really significant difference in June and July, 1 year after amendment. There's 1 year, but this is, I would say, this is a consequence of the variation. The soil respiration and microbial biomass, we also looked at this. Again, the soil respiration from previous slides, you saw it depends on soil temperature. So if you take this upper figure A here and compare it with C, A and B is together, is the consequence would then be C. So the temperature is important, but also, of course, the soil moisture. If it's a condition of drought, which was obviously here in August, the respiration is also going down. For microbial biomass, we looked at microbial biomass carbon and nitrogen. We didn't see a significant difference between control and biochar amendment. What is also interesting is soil water content and temperature sensitivity. While biochar, because it's a porous structure, increased soil water content, we didn't really see a main difference in this temperature sensitivity. Interestingly, it was higher at 5 tons, but at 10 tons it was then close again to the control. We couldn't really explain this, and we have to look at this in more detail. So let me come to my conclusions. The results that showed us so that we can draw from wildfires and from artificial pyrogenic carbon amendment are, in a very technical sense, in a very narrow sense, and framing, quite positive. But at the same time, we could still not say enough, and this is because the underlying processes, especially in combination with thermophos thawing, are difficult to address. What we found is that increased an increased carbon stock in the organic layer, both from wildfires and from additional artificial carbon as biochar, because it's recalcitrant, but this is exactly the amount that was actually added. Effect on pH, soil pH was only marginal and also not lasting. There was no clear and consistent tendency towards increased soil carbon CO2 efflux. During the first months, biochar amendments increased soil temperature. This is an albedo effect because the surface is dark. This is true for wildfires and for the biochar amendment. The treatments did not significantly influence soil microbial biomass or carbon and nitrogen. Biochar amendment had no significant effect on biological nitrogen fixation rate, which is also an important aspect. So the microbial, not only the biomass, but also the functions didn't really change significantly. Biochar treatments did not include statistically significant effects on net nitrogen mineralization, ammonification, or nitrification rates, which underlies this. The pyrolysis temperature did not have a great effect, but this is just detail here. So in conclusion, biochar amendment in forests, in boreal forests, is only a safe strategy as long as the fire regimes are stable. If more severe fires occur in period of drought, boreal forests may become a massive carbon source, because such strong fires then of course also consume this recalcitrant carbon because it sits, as we saw in this picture, in the topsoil, so the interfere zone between organic horizon, which is eventually completely burned, and the mineral soil horizon. With this, I would like to thank you for your attention. I would like to thank Interact for providing access to these research stations, and thank you to all colleagues involved. And I would leave you with some reading suggestions. We published recently a very nice volume on global change and forest soils, where much of this presentation is available in a chapter. If you would like to know something more related to biochar supply chain cycles, then I would suggest our book published in 2016, A Biochar Regional Supply Chain Approach in View of Climate Change Mitigation. Thank you very much.
Thank you very much, Viktor.